Hi all, Dr. Clark here again. Today I'm going to lecture on the field of population dynamics. And so we're going to look at, just in general, we're going to look at how populations grow, the two main different ways, one which we call exponential growth and the other one we call logistic growth. And then next lecture, we're going to talk about how populations are regulated. And then the final lecture, we're going to kind of in population dynamics is we're going to talk about how humans conserve populations. So conservation biology of populations. All right, so the first thing that I want to talk about is human populations, because a lot of people find them really interesting. I find other organisms far more interesting than humans, but I find the dynamics of human populations kind of interesting. So if you look here, you can see this colored map of the world, at least the terrestrial habitats of the world. And then on the right hand side, there's this key. The different colors indicate the percent of population growth in a year. So the percent of that population that's going to grow. So everything that's in purple, so Siberia, Greenland, parts of Africa, the southern tip of Africa, have no growth. Okay, they might even have minus growth in these regions, so negative growth. Anything that's in purple is little growth, so it could have no growth, or it could be up to 1%, but not surpassing 1%. Light blue is 1%, 2%, and then 3+%. And so if you look at this, you can see that the majority of the terrestrial habitat, majority of the planet, is growing population-wise for humans. You have these areas like the United States and Canada that might have small amounts of growth, or they might be stable and not growing at all. Same thing with Australia. But huge swaths of the planet is growing, in some people's opinion, at an alarming rate. So let's put this into perspective. If we look at the world's population, say, in the 1940s. In the 1940s, the world population was just approaching 2 billion people. So from 1940 to present day, so let's just say, it's 78 years, but let's just round it up and say 80 years. So in 80 years, we've gone from 2 billion people on the planet to 7.7, a little bit more than 7.7 billion people on the planet. We've added almost 6 billion people to the planet in 80 years. That's an alarming rate. Most people have grandparents that are 80 years old, or parents that are 80 years old or approaching 80 years old, and would remember when the planet had 2 billion people on it, and now when the planet has almost 8 billion people on it. So with that, we have resource issues, and that's kind of the general premise to this course, is that we need to manage natural resources. Some individuals think we need to manage populations of people, maybe. I'm not going to get into talks about people management or people population management. There are countries, this one in particular, you see there's no growth or very low growth because they have population management regulations. So they regulate, how many children can be born to a family. Now, that regulation has expired, and it depends on what city you're in. If you're, if you're in China, it depends on where you're at, whether or not there's still a cap on number of offspring that you can reproduce. The United States has about the same growth rate as China, population-wise, but we don't have a cap on number of individuals. And you might ask, well, why is that? Well, the reason for that has to do with this graph. Developed countries tend to be more educated, and they tend to be less likely to over-reproduce. Okay? So again, if you know much about population biology or much about biology, you know that it only takes two individuals to replenish the parents of the children. So two children replenish the parents. Or if you're a single parent, one child. So that's all it's need to keep your population stable. The United States has been growing their population, but it's a fairly slow growth rate. Right? We're at 350 million people in the United States. We're the third largest country in the world. But we've been at 350 million for about 10 years. So give or take a few million people. But it's been pretty stable. And even before that, maybe even for 20 years, we've been fairly stable. We've probably been at 300 million for probably 30 years. And fairly stable at those rates. Now, so our population is growing, but very slowly, because we've been a developed country for a long time. Less developed countries, like the ones that you saw on the map, that, if we jump back, that are in these threes or twos, most of Africa, some of the Middle East, they're going to over-reproduce. They're going to have a lot more offspring because, first of all, they have a much higher death rate in their offspring. Secondly, if they're trying to develop, they're typically trying to develop from a farming or physical labor industry, and the more kids you have, the easier it is to make money, per se. And then again, there are less education. We've seen that education is one of the key components to preventing over-reproduction. Now, I'm not saying anything about individuals who have big families and things like that. It's your right to have big families. I'm just saying, in general, when we're talking about population biology, if you reproduce more than two offspring, you're contributing to the population growth rate in the world. If you're contributing only two offspring, you're just replacing yourself and your significant other, and the population stays stable. If you choose not to reproduce at all, then your contribution is negative to the population growth. And that's all there is to it. Okay? I'm not saying things about individuals who decide to have, 6, 7, 8 kids. In the United States, the nice thing about that's your right. You can do that. In other countries, that's their right. They can do that. And that is where you see these big bubbles of population growth. Developed countries are growing. We expect them to start teetering off. So they've been growing since the 1750s, but we expect them to kind of start to drop off. Most of Europe's dropped off, and lots of Europe has negative growth. The United States has a little bit of positive growth still, Canada positive growth, but it's these less developed countries where the populations are exploding. as they develop, more than likely they're going to fit into the developed country, and their population growth will start to decrease because they've created the industry where they don't need labor, and they don't need a lot of children to work the farms or work manufacturing jobs and things like that. Instead, they, they're going to have a drop in their number of offspring that they need to have, and you'll see that they're more like developed countries. At one time, the United States was a less developed country, and people were reproducing a massive number of offspring. If you ask grandparents or great grandparents, if you had the opportunity, how many offspring were in their family, it's probably far more than what's in your family currently. And so, especially if they grew up in the Midwest, where it was really common to have 12 children or more if you're working a farm. Same thing in less developed countries. So that's where that population increase is coming from. Now, we're sitting right about here, okay, close to 2020. Believe it or not, it's kind of scary for some of us that, were born on the other side of 2000, that we're already to 2020. But, we're sitting pretty close to that 8 billion people mark. Right? Most individuals are going, I shouldn't say most, a lot of individuals that are watching this video are going to creep up on that 2050 mark. You'll probably be alive in 2050. That's probably where we're going to reach at least 9 billion, if not higher than 9 billion. Once you add the 2 in, we could be closer to 10 billion. We'll talk about carrying capacity of the human population. There has been quite a bit of research and quite a bit of information out there that suggests that a population of humans at 9 billion is the maximum that the planet could hold under our current situation. Like how much fossil fuel we burn, how much food we eat, the roads, the buildings, how we construct everything, our technology, whatnot. At about 9 billion is the max. Now, we'll see if that's true, obviously, because we're going to make it to 9 billion. But we'll see if that's true, and I'll show you how other populations are regulated by similar things. All right. So let's start describing growth, population growth mathematically. So it's really simple. First of all, N, capital N, is the total number of the population. And the population is dictated by a single species living in the same area. In the case of humans, our N is 7.7 billion people. Now, in other cases, like if we're talking about fish species, or we're talking about amphibians, or we're talking about things like that, that don't have the ability to move all over the world, they might have multiple populations that we need to talk about. We'll approach that when we get to an example. The rate of growth is the number of individuals in a population that can be reproduced. And this is under maximum conditions, ideal conditions, so plenty of food, water, space, energy, no problem with the number of eggs produced or number of sperm produced, anything like that. So there's no limit. R is the rate that you would expect for a given species. Time is whatever time to maturation, or time to birthing, or time to hatch, or whatever it might be. It just depends on the organism and how many offspring they have in a given time. So if we're talking about like bacteria, we might be saying, all right, we're talking about the number of bacteria that you can reproduce in a week. If we're talking about mosquitoes, we might be talking about the number that you could reproduce in a month. If we're talking about humans, we're talking about the number of offspring that you could potentially produce in a year. And so that really depends on the organism. Now, this can be simplified and put into this equation, which we call the geometric rate of increase. And so this is the ideal population increase. N is the population size at a given time. Okay? N naught means that there is no limitations. And you're just going to take that N and you're going to times it by the rate of the population. And then you're going to raise that to T. So if they can have, if an organism can have 4 litters a year, or 4 batches of babies a year at 4 babies, so you're going to raise that to 4, and then you're going to times that by the beginning population. This is what we call exponential growth or exponential growth rate, and it is a constant rate over time. There is no limitation. This is an initial growth rate. We're going to look at this in a second. Okay? We're going to look at an example now. If you start with, say, a pair of cockroaches, so you got 2 cockroaches, and that female cockroach can reproduce 10 offspring. Every 3 months, she can reproduce 10 offspring. We can calculate what or how many offspring 2 cockroaches can reproduce in 1 year. So let's do it. Okay. So let's first start with the initial time 1. Okay. So this is the first 3 months. You have 2 cockroaches. Okay. The rate of increase, the number of offspring, 10. So just 10 times 2. Now you have 20 cockroaches. Time 2. You have that 20, still 10, so now you have 200. So if those 20 are going to reproduce, 200. Now, this is not taking into account that some of these 20 could be males. We're just assuming that, these 20 are going to be females, and that this original 2 are females. And so, because males are not reproducing, so let's say we have 4 cockroaches, and 2 of them are female. Okay? This is just hypothetical. Now your population is 200, so this is the third set of 3 months times 10. Now you're at 2,000 cockroaches, and then the last one you take 2,000. Now you're at 20,000 cockroaches. So we're talking about 4 cockroaches in 1 year's time can produce 20,000 offspring, 20,000 cockroaches, potentially. Right? And so this would be the graph that you get from that. You would get at time 0, you start with 2, it's barely a blimp on the graph, and then you just have this exponential growth rate where it's exploding, and you just get thousands of cockroaches in one given area. Because most of the time you're not starting with 2. Okay? So you get this huge explosion. Now, the issue with that is that growth rate is what we call exponential growth rate, which means that there is no cap and there's no shortage of food or space or no issues with reproduction, 2 individuals can't reproduce kind of thing, nothing. So under normal conditions, though, this wouldn't occur, and we'll talk about that. Okay? So that showed just a 4 kind of period of time. Now, the other thing that exponential growth is about is not 4 periods. There's no stopping. So those 20 individuals that were reproduced at the first, some of those are going to reproduce in month number 1 or month number 2. So you wouldn't get this huge increase 1 point at a time. You get an increase, a constant flow, a continuous flow of the population up. To describe that, we need to just use a different formula, okay, where you're looking at delta N and delta T, or the change in population divided by the change in time, okay, is equal to the rate, so how many offspring can you reproduce, times the original population. Okay, so again, D is equal to delta, represents change. So the formula would read, the change in the population per change in time is equal to the rate change times the population size. R is not a constant. R can change over time and may change over time. And we'll look at situations where it does change over time in the next lecture. Okay? So that simple mathematical equation is known as the exponential growth equation, or the exponential growth model. Now, again, can be represented just like this. Change in number of the population divided by change per time is equal to the rate of increase times the population. The issue, or maybe not an issue, this is a really good thing, especially if you're dealing with cockroaches, is that exponential growth will always have a limit. So where you saw that graph of cockroaches going straight up, eventually it has to crash, or eventually it has to peter out, and it has to level out. Because exponential growth is, again, it's maximum likelihood that a population would increase at that rate. So it's based on food, shelter, water, mate selection, no predation. All these limitations that would limit the growth of a population, they're absent, and so it's maximized. So really no population in the wild ever has exponential growth for very long. They might experience it initially, so like a cockroach makes it into a house that's abandoned and there's food, that might give you exponential growth at first, but eventually the food's gone, and that population is going to crash. So shortages of food or other resources, or increases in predation. We often see this the case, especially in wild species, where you might have introduction of a new species that comes and their population explodes, and then the predators follow and they start bringing that population back down. All right, so let's look at a little bit more terminology that's describing real world, real example populations. The carrying capacity, which is often just denoted as K, is the number of individuals that a given area can support. Okay? And so, again, like I said, for humans, there's been quite a few calculations that the human carrying capacity of the planet is about 9 billion. Now, there's other estimates that suggest 12 billion, okay? But nonetheless, we know that there has to be a carrying capacity for this planet. There is a number that humans can reach in which we have now depleted all the available resources. Overshooting. That's when a population goes past the carrying capacity. So there is a level at which organisms can sit and not completely deplete the available resources. When a population overshoots, that means they go past that carrying capacity. Most of the time, that results in a population crash. So what happens is you over-reproduced, and now you've ate up all your resources, and the population has a severe crash, a severe rollback. Now, that could be due to no food. It could be due to increase in disease, no shelter, lack of water, increases in predators. There's all kinds of things that can have this direct effect and make the population crash. And then you can get into what we call boom and bust cycles, and this is often different species of organisms will often fit kind of a boom and bust um, cycle, and that would be cockroaches are a good example. Their population explodes and then crashes, and then their population explodes and then crashes, and then explodes and crashes, and on and on and on. And normally that's the result of food availability when it comes to like cockroaches. Other species that might not be the case, and we'll look at some specific examples of that. Okay. One example that is been going on for a long time is the research that's done on the Isles of Royale. And so this is Lake Superior, and there's a series off the coast of Michigan, or the area of Michigan. There's a kind of band of land. It's an island, but it's, you know, depending on the water, there are maybe multiple islands, small islands that are kind of attached together in an isle. And researchers have been looking at the cycles of moose and wolves on these islands for a long time. So from the mainland, moose have been able to get in onto the island, and also wolves have followed them out. So they've, you know, swam across this channel from the mainland onto the island. And researchers have been looking since the 1960s. They've been tracking populations of moose and population of wolves on these isles, or on this island series of islands. And, you know, they've documented, you know, wolves feeding on moose. You can see these two pictures here. And what you see when you look at the numbers is you see this cyclic kind of boom and bust situation with the moose. So when moose first originally got to the island, their population exploded. There's nothing out there. There's no rabbits. There's no competition for food. So their population exploded. Okay? They overshot their carrying capacity. So you had this population crash, and they died back. Okay? And they've done this many, many times. Now, the carrying capacity can change over time, depending on the ability for plant communities, or the ability for, you know, habitat to respond or rebound. So a carrying capacity can move over time. If you get droughts or things like that, you might have a carrying capacity that takes a dip. If you get a wet season, carrying capacity could increase, and so therefore these organisms can match that carrying capacity, or maybe they can overshoot a little more if it's a wet season than what you would expect. Okay. So that's kind of the cycle that the moose has had on these isles. Now, definitely a player in this are the wolves. So the wolves can help with this dieback. Okay? And so as the moose population rises and gets big, the wolves can come in and knock the moose population down. And if you saw the wolf population, you would see something that fits this curve a little bit like this. So the wolf population would come up, and then as the moose population dies down, the wolf population would follow. And so you would get this inside, just to the right of that curve, you'd see the wolf population going up and down, because as the moose population increases, the wolf population has, you know, a year, maybe 2 years, to then increase and knock them back down. And then as they knock back down, they have 2 years or so to die off, and then back and forth. So resource scarcity slows exponential growth. And so you get these areas where either food is scarce, or habitat is scarce, or water is scarce, or predators increase, and that really can change the population dynamics and make species teeter around the carrying capacity. And so we call that a sigmoidal or an S-shaped curve, but it's really just a logistic growth curve, and it's represented by this equation here. So again, delta n, or the change in the population divided by the change in time, is equal to the rate, so the rate is still there, times the population. But now you have this other piece of an equation where you're looking at k. Now you're putting in a known or calculated estimate that given area can support. So now everything is really based on k. So how many organisms can that area support? And that's based on k. So here you can see the wolves will do something like this. Population is low, start increasing, and then as they get close to the carrying capacity, and this depends on the area, as they get close to the carrying capacity, they will slow down. Their population growth will slow down. There's less nutrients, there's less resources, there's more competition from within. So the number of offspring that are reproduced, the number of offspring that survive starts to decrease. And you can start to see that the wolves will sit there and bounce around that carrying capacity. Now in some cases they overshoot it, and they'll have a population crash, just like the moose population and some of the other populations that we'll see. Okay. So again, this is the equation. So another way to write the equation is growth rate is equal to the rate of increase times n, okay, and then k minus n divided by k. And the reason why we do this is that as n and k get close to each other, the growth rate begins to slow. When n is equal to k, the growth rate is going to be 0. There's not going to be any growth rate. Again, the k can change though, and does so often. And that will, give us these kind of growth curves. So an exponential growth curve, which I was showing you from the exponential equation, where this is gone and it's just r times n. That's an exponential growth curve. There's no component, no resource limiting factor in an exponential growth curve. So you get population explosion. Now, again, there is no such thing as a population that will always be in an exponential growth model. They will eventually have a carrying capacity. So all exponential growth models will turn into logistic growth models because a carrying capacity will eventually be reached. Now it may take a long time, and you might get huge population sizes, but eventually this will turn into a sigmoidal curve, and so the J-shaped curve will eventually become an S curve, and you'll get a logistic growth model. And we'll calculate some of these and look at some more examples when we go to the next section, when I start talking about, well, what can limit the growth? What is the factors that limit the growth and the main players in a growth equation? All right, so we'll stop there, and next time, again, like I said, we're going to talk about growth limitations.